Hello folks, today we're going to look at logistic regression using ArcGIS and our statistical software. My name is Chad Goings. I work for Rolling Hills Consulting Services out of Washington, Iowa. My number is 319-461-7427, and you can feel free to give me a call if you purchase this course at any point, and I will take you through any questions you might have. So what you're going to need for this course is you're going to need ArcGIS and you're going to need the Spatial Analyst extension. So hopefully you have that. Now our statistical software is free to download, so you can get that if you don't have it. So no need to worry about that. Okay, so when should I use a logistic regression? So you may ask yourself, not the 80s song, you may ask yourself, you might ask yourself, the first question might be, is my dependent variable dichotomous or binomial, or that's the fancy words for it, but basically does it just have two options? Is it a yes, no, there, not there kind of situation? So if that's the case, then that's what a logistic regression is all about. It's where the dependent variable, or what it is that you're trying to model, only has two categories. So kind of a yes, no, there, not there. So in GIS we think more of a there, not there kind of thing because we think spatially. But so one example, maybe a non-GIS example, would be kind of an epidemiological situation where a person either has a disease or doesn't have a disease. So the disease is either present or there, absent or not absent, that sort of thing. The example we're going to use, and one that I'm most familiar with, is archaeological sites. So basically, is there a site on this particular piece of property, or is there not a site? And so logistic regression works well for that case as well. And so that's going to be our case study and what we're going to use to kind of demonstrate the steps, the process that's involved in doing a logistic regression. So one way you might think of it as a checkerboard. So as GIS people, you might think raster right away. So this is think of the checkerboard as a raster grid, and within each square, you either have a checker or you don't. So there's either a checker present or not present. So present, not present, not present, not present, present, etc. So that might be another way you could go about thinking about this. Kind of think of a raster grid. Is something there or not there? So maybe I'm from Iowa, so you might think of the state of Iowa, and you lay a grid over it at whatever resolution, and you say, okay, there are archaeological sites in Iowa. We know certain ones are here, so we put an X in this square, an X in that square, so we know where certain archaeological sites are. What's going on at those particular locations that aren't at other locations where we know there's not sites. Okay, so that's the first question. The second question should be, or you might think of, are my independent variables, or those things that I think explain why sites are where they are and why they're not there, are those continuous variables, categorical variables, or both? Because logistic regression can handle all three. You can use all continuous, all categorical, or a mixture of both. So that's kind of nice. Just to kind of give you a little bit more background on that, continuous, when I say continuous, and you might think raster, so something that changes continuously over the landscape, something like slope maybe. So imagine walking out, you're on a low slope, and then it changes gradually as you're walking. So those things change continuously over an area. Whereas something like soil type might be mapped as a polygon or a categorical data. So when you think categorical, you might think vector data, like polygons and points. Okay, so some of the variables that, some independent variables that we're going to use and that are important for where archaeological sites are things like distance to a major water source, slope. So both of those are continuous, because as you're, for instance, distance from a water source, it continuously gets further and further away as you move from the water source. Soil type, again, could be categorical, so maybe archaeological sites are found in certain soil types. Relief, so sort of related to slope, but so is this, but looking more at it, the area rather than the particular location. So within a certain boundary, is there a lot of up and down topography, or is it flat, that sort of thing. Okay, so now what? We've answered these questions of, is my dependent variable binomial or have two categories, and are my independent variables both continuous and categorical? So we can use a logistic regression. Now we need to capture these variables in GIS. And so again, you've got your vector data format, points, lines, and polygons, and your raster format, grid. Okay, so continuous variables, again, are best represented as raster grids, and your categorical variables are best represented as points, lines, and polygons. So your dependent variable, again, has two outcomes, and your independent variables are going to be either continuous or categorical. So your dependent variable in a logistic regression is a lot of times best captured as a point shapefile. So in this case, we're going to use a point shapefile to locate with an XY coordinate where an archaeological site is. So we're going to capture where known sites are using a point shapefile in ArcGIS. So come back to our checker grid. Again, yes, no, present, not present. You might be tempted to use a polygon to capture your dependent variable. So if you think about an archaeological site, a lot of times they might be represented as a polygon because you might be finding artifacts over a big area. You don't want to use a polygon, however, because it'll violate some statistical assumptions, and I'll explain that here. Some of you may have heard of spatial autocorrelation before. And it's basically a value that tells you how similar things are that are close in space. And typically, to kind of paraphrase the first law of geography, things that are closer in space are more alike than things that are further apart. And so the reason you don't want to use a polygon is because all those values that are within that polygon are usually all going to be similar values just because they're close to one another. And in statistics, you don't want to have that type of correlation between your sample points. So let me give you just a kind of an example here. Like, say you have a tree and you're going to measure the distance from a tree. So you take your tape measure, put it at the tree, you walk out, and it's 10 feet. Now say you're going to move to the left a couple paces. You can pretty much guess what your still might be at 10 feet, or depending on if you went forward or up a little bit. But basically, you don't want to be able to guess what that value is. They need to be, for the statistics to be correct, they need to be independent of one another. And so just based on the spatial aspect, there's a similarity between points. And so you want to use points for your dependent variable. And not only that, but you want the points to be somewhat separated from one another. So you don't want to use a polygon, and you don't want to have a point here and then a point a little bit away from it because most likely your values are going to be similar. So we're going to just pick a random watershed, and so this is your watershed boundary. I superimposed a grid over it, and so we can kind of think of this as like our checkerboard. So within each of these squares, is there a site or is there not a site? And so we're going to use points to show where sites are located, and I just made these sites up just for this exercise. And so we've got 33 points here within this watershed that show where sites are located. Again, I made up where these sites are, so there's not really sites in these points. But for our purposes, there are. Okay, so we know the green dots are representing where sites are. What's going on within those grid cells to make the sites be there compared to the rest of the grid cells? That's what we're really asking, so that we can know why the sites are where they're at, and then also that we can go out and maybe find new sites based on cells, grid cells that have the same thing going on within them. So we're going to just use continuous variables as our independent variables. I typically just like to use continuous variables compared to categorical because continuous has an advantage in that you're not really losing information. But in mathematics, if you take something that's continuous and you break it up into categories, you're kind of losing information. And so we're just going to stick with continuous variables for our independent variables, and we're going to use distance from a major water source, slope, and relief. And so I'm going to provide these grids for you, but if you're doing something similar to this, I'm going to assume that you know how to, in ArcGIS, know how to do a distance to water, or know how to create a slope grid or a relief grid from a raster or a digital elevation model. And so here are our three independent variables captured in or modeled in ArcGIS as a distance to water grid, a slope grid, and a relief grid. So again, we're using continuous variables, and we want to be able to extract out the background to compare that with the known site points. And so in order to do that, we're going to use a systematic sample across the watershed to pick up the variability that's going on in terms of those three variables: distance to water, slope, relief. Okay, so there are 33 of these site points. It's always a good idea so they are our dependent variable. It's always a good idea to have the same sample size where possible for your independent variables. So we're going to come up with 33 background points, or what we might call non-site points. And the way we're going to do that is we are going to use the fishnet tool in ArcGIS. And so we're going to go to the Arc Toolbox, we're going to go to Data Management Tools, Feature Class, and then create Fishnet. So we have to save, say where we're going to save it. We want the extent to be the same as the watershed boundary. So we're going to create systematic points across that watershed boundary. So our template extent is going to be the same as the watershed layer. You might want to mess around with this cell set size, width, and height to get to where it'll make your points the amount that you want and the spacing that you want. So I just came up after messing around with it 2500. And then you also want to make sure that your geometry type here is selected as polygon. So this is what you end up with when you use the Create Fishnet tool. And so we're only interested within the watershed boundary here. It used the entire extent of the polygon. So we're going to select the background points that are within the watershed boundary polygon, and you can just manually select them using the selection tool in ArcGIS. And then we're going to export those background points. And so now we have our background points and our site points, and we're going to compare the values, the raster values at the background points compared to what the raster values or the grid values are at the site points or the known archaeological sites. Okay, so how do we do that? You may ask yourself, again, not the 80s, you may ask yourself, why such a big house? Well, kind of sounds funny, but you know. So we're going to use, in order to extract those values, we're going to use the Arc toolbox, go to Spatial Analyst Tools, Extraction, and then extract multi-values to points. So here it is. This is what it looks like. We're going to do that for both the background points and the site points. So for input point feature, easy for me to say, point features, we are going to choose background site points first, and then we're going to enter our 3 raster grids here, our slope, relief, stream distance, and it is going to output the cell values into the point shapefile. So we do that for the background points. So here, like say I select this particular point here, you can now see in the table that it tells you what the relief value is at that particular location, what the slope value is, and what the stream distance value is. And so you want to do that for both the background points. You want to run that tool on the background points and the archaeological site points. So use that extraction tool on both. So extract values from multiple raster grids, and first you run it on the background site points, and then you run it on the archaeological site points, and then you'll have 2 tables that show you the values of the 3 independent variables at sites and at background. And then once you've done that, we need to export both of the tables. So we'll open up their attribute table, and we'll go to the drop down here on the attribute table, export, and we're going to export both tables as a DBF. So you'll do that for your background points, and you'll do that for your known site points. Once you've got that, you want to open up those tables. Most of you probably have Microsoft Excel, but it doesn't matter what type of database software that you use, but you want to open up those database files. And when you do, you'll see, so here is the background file. You'll see ID is 0. You'll see all the relief values at those points, all the slope values, all the stream distance values. You're going to have 2 tables, one for background points, one for site points. Then you want to take those 2 tables and make them into one. So you want to copy and paste the values out of one and put them underneath the values in the other. So here, up above, we have the background site points. Down below, we have the archaeological site points. And to differentiate between the two, we're going to take the ID field and we're going to give the background points an ID of 0 and the archaeological site points a value of 1. So you've got all your 0s here, your background points, all your 1s are your site points, and then you've got what the relief values are, slope values, and stream distance values are at each of those locations. And you'll want to save this as a CSV file, so a comma separated value file. So when you go to save this, you're going to save it as a CSV, comma delimited, and call it, I'm going to call it log reg, L-O-G-R-E-G. You can call it whatever you want. So now is when we're going to bring that table into our statistical software. And so our statistical software is a free software you can download Here's the website. I'm going to provide the PowerPoint slide so you'll be able to see that up close. And you'll go to this site, you'll download our statistical software. And once you get it downloaded and installed, this is what it looks like when you open it. And it starts right here with command prompt. The first thing you want to do is set the working directory. So to do that, you use the command set wd, and then in parentheses and quotations, you put the working directory of where you saved your data. So in this case, most importantly, where you just saved that CSV file. So this is where I saved it, on my C drive. Yours is going to be a little different, I'm imagining. So whatever directory you've saved it in is what you want to put in between these quotation marks. Okay, so we told the working directory, we told our statistical software what our working directory was or where it was. And so let's see if it worked. Let's type in get wd and then empty parentheses, hit return, and it should come up with your working directory that you typed in. Again, it's going to be different than the working directory that I'm using. Okay, so the next thing we need to do is bring in our table that we created in Excel. Now we saved it as a CSV file, comma, separated value file. So we're going to bring it in by typing log_data. That's just a arbitrary name that I gave to tell our statistical software that's what we're going to call this table. So we say read.table, and then in parentheses here, you're going to, inside the quotation marks, you're going to put the name of the table that's in that working directory you just set up. So you saved that Excel CSV file into your working directory and you called it something. I called it logreg.csv. So that's where I'm going to tell our statistical software that's what it's called, that's where it's at, separated by commas, and it has a header with the ID field, relief, slope, stream distance. Okay, so now that R knows where the working directory is and it now has read our CSV file, we're going to find out if we've done everything all right so far by calling up the table and seeing what the headers are, see if it read everything correctly. So we're going to say names, and then in parentheses log data, which is the name we told, the arbitrary name that we told our statistical software, semicolon, we're going to get the dimensions of the table by putting in dim, and then again the name of the table. And so once you hit return on that, it's going to tell you the names of the headers in the table and how many rows and columns the table has. So I'm providing this table for you. You can also, as you go through the steps, export it yourself, but this table has 66 rows and 4 columns. So the 4 columns are the ID field, the relief, RLF, the slope, SLP, and the stream distance, TRMDST. Okay, so now we have the data in R. Let's do some modeling, shall we? Okay, so we're going to do our first model in our statistical software, and we're going to call it Model 1. So we're going to type in Model 1. We're going to give it one of them little symbols there, which is necessary for our statistical software. And then GLM stands for a general linearized model. And in parentheses, we're going to put ID, which is our dependent variable. So it's the field that has the zeros and ones. Zeros are the background points. ID of 1 is the site points. Then we're going to put one of those, and then we're going to do relief plus slope plus stream distance, comma. The table is data equals log data. That's the arbitrary name we gave it. Family equals binomial, because it's a binomial dependent variable, 2 categories. Okay, so now that the model's in there, let's see what it came up with. So we'll do summary, and then in parentheses model 1, which is what we called the first model. So here is the output that we get. It's calling up the model that we did, so showing you the formula that we used. And the area you're going to pay most attention to is this area right here that I've highlighted in yellow. So this is going to show you your coefficients and or the independent variables that you used. And then a really important part is this part right here with our z-values and our probability scores, showing how much these particular variables are explaining the difference between why a site is there and why a site is not there. And so you look at these little asterisks here. If you get one asterisk, then that means it's statistically significant to 0.05, 2 is 0.01, and 3 asterisks are 0.001. So basically the more asterisks, the more statistically significant that particular variable is. So the relief is very statistically significant with 3 asterisks, slope has 2, and stream distance has 1. Another thing to look at here is these the coefficients, which is given right here. If they're negative, then that means as that value increases, the chances of a site decreases. So stream distance, as you move away from a stream, the less likely of a site. Slope, as your slopes get bigger, less likely of a site. Relief is the opposite. As relief increases, so does the chance of a site. And you notice there's no negative sign before relief. So that's another thing you can look at. So if you see a negative sign before your coefficient for that particular variable, that means as the numbers increase, the chances of that particular phenomenon being present decreases. So all 3 independent variables are significant. So let's map them out in ArcGIS. Okay, so we're going to take it slow. You could probably, after you go through these steps, you could probably say, well, I can turn this into one big formula in the raster calculator, but I'm going to do it kind of a step-by-step process. And so we're going to use the raster calculator. So again, you need Spatial Analyst, and you go to Spatial Analyst Tools in Arc Toolbox, and you go to the raster calculator. And the first thing we're going to do is we're going to take each independent variable grid, so relief, slope, stream distance, and multiply it times its coefficient that we got from our statistical software. So we'll bring in the parentheses for everything, and then relief times its coefficient plus slope times its coefficient plus stream distance times its coefficient. So that's the first step we want to do, and then the output we want to call step 1. So the next thing we want to do, so we've got a new grid now that we just created called step 1. To create step 2, we want to add the grid step 1. We want to add the intercept to what we just created. So step 1 plus 20.662592, which is the intercept that we got from our statistical software. So we're going to call this step 2. Okay, so now that we have step 2 created, we're going to get the exponential of that step 2 grid. So we double click on EXP over here, and we tell it we're going to do that on the grid called step 2, which we just created, and the output is going to be called step 3. Okay, so step 3 is you could kind of consider that grid as an odds grid. So what are the odds of a particular site being located there? We want to change the odds into probabilities and scale it so that we've got 0 to 1, where 0 means that there's low chance of a site, 1 means high chance or more suitable. So we want to do step 3 plus 1 and call that step 4. Then we want to divide step 3 by step 4, and this, we're going to call that model 1 because that's going to be our final grid. So here should be what the final grid looks like. So here, your grid is going to go from 0 to 1. So again, the values that are closer to 0 means that there's less likely of a site being there based on the data that you used. And the value that's closer to 1 means that you're more likely to find a site in that particular grid cell. And so I broke up that particular grid, the final grid that we created, into 3 classes using the natural breaks classification scheme. And so the white that you see here should mean that there's low probability of finding a site. Gray means there's a medium chance, and black means that there's a high chance. You can see the green dots are where the sites are that we used, and a lot of them are in the black, some in the gray, and fewer in the white. So we can run some histograms to see how well we did. So if you turn your site points into graphics by right-clicking on the archaeological sites file, right-click, convert to graphics, and then if you select the graphics, you can run a histogram using the Spatial Analyst toolbar, and it will just show you the values at those points. So we had, remember, 33 site points, 21 of them are in the black area, 8 are in the gray area, and 4 are in the white area. So most of them are in the black where we want it to be. Now keep in mind that we're testing the model with the same points that we used to create the model. Ideally, you would want some additional points that are independent of the model, were not used in the model, to verify this. And so if you can leave out some of your points in the very beginning and use those later as a check, that's the best thing to do. Another thing to consider is how much area are you mapping as high probability. So, if that whole watershed was black and a little bit of gray and a little bit of white, of course, just by chance, the site points are going to fall in those black areas. So the thing to look here is that most of the watershed is mapped as low. Most of the watershed is mapped as low. The next is moderate, and the smallest amount of the watershed is mapped as high. So if this number of sites is high and this is low, that means you're mapping a low area as high probability, and all your sites are falling in that smaller area. Okay, so there's free tech support on this class, so if you have any questions, you can email me is the best. So cagoings@rollinghillsconsulting.com, which you should be able to, I'll put it up nice and big for you there. You can also call 319-461-7427. You're going to have to give me 24, 48 hours maybe to get back to you, but I'll try to get back to you as soon as possible. And I'll answer questions that are related to this course to get you through the steps if you have any questions. So I hope you learned something from this course. I hope that you can use this for your own data, your own modeling purposes, and that it was helpful for you. And feel free to get in touch with me, even just to let me know if you like the class, or any kind of feedback is welcome as well. So thanks, and have a good rest of your day.